All right, welcome everybody. Welcome back from lunch. I hope you enjoyed. Our post-lunch speaker will be Lukas, telling us about how to evaluate blame for gradual types. Take it away.
All right, thanks. All right, so this talk is going to be about this research question. How does gradual typing help with debugging mistaken type annotations? And by gradual typing here, I mean any language that lets programmers mix typed and untyped code. And here's a little sneak preview of where we're going to go before I kind of slow down a little bit. In this work, we're interested in investigating this question empirically. So we're interested in looking at how implementations of gradual typing behave in the face of real programs. And while the first way that might come to mind to do that is a user study, we investigate it from a completely different angle. So that's a little sneak preview to whet your appetite. But for now, I want to slow down a little bit and talk more about the context. And in particular, I want to talk about TypeScript, which is probably the most well-known success story of gradual typing. We had a keynote about it yesterday, so we should all be somewhat familiar. But in case you missed it, TypeScript is a language that adds optional type annotations on top of JavaScript. And it's been widely adopted. A whole lot of new code is being written in TypeScript these days. And naturally, developers writing that code want to be able to reuse code from the extensive JavaScript ecosystem, the world of NPM packages and so on. But making that connection from the JavaScript world to the TypeScript world presents a problem. Because in order to maximize the usefulness of TypeScript's type checker, those libraries, or at least their APIs, ought to come with type annotations. And the TypeScript community has come together to try to bridge this gap by creating this thing called definitely typed. So what is that? Essentially, definitely typed is just a crowdsourced repository of type annotations. They're called type declarations, or I like to call them type interfaces, because they essentially describe the interface of a library. So for example, a sorting library's interface might look something like this, saying that it provides one function called sort, which accepts two arguments. The first one is an array with anything inside. The second one is itself a function of two arguments that returns a Boolean, the comparison function. And then the result of this sort function is again an array. Now here's the interesting thing. This interface was crowdsourced by the thousands of contributors to this definitely typed repository. Meaning, it probably wasn't written by the original author of the library that it's referring to up in the JavaScript world. And in addition to that, it lives in a completely different place here on this definitely typed GitHub repository. So what I'm getting at is that it's quite easy for this process to result in mistakes in type annotations. For example, it might be that the actual sorting library in the JavaScript world expects the comparison function to return an integer instead of a Boolean, like for some 3-valued comparison. And in this way, you'd have a bug in the type annotation in this type interface. And indeed, there's been a substantial amount of work in the PL community identifying and analyzing these kinds of type interface mistakes. And besides observing that they do indeed happen, and pretty frequently, another common theme across this work is how subtle these mistakes can be. Being tricky, avoiding detection for a long time, difficult to debug when they eventually do arise, these kinds of things. Now, of course, we, the academic community, have opinions about the source of this problem and how to address it. And one significant argument here says that really the trouble is that TypeScript is an example of a style of gradual typing that uses the erasure semantics. So in other words, type annotations in TypeScript are used for some best effort error checking before you run the program, but then they're thrown away and the programs run as if it were fully untyped JavaScript all along. So the language is not doing anything to ensure that at runtime, values in typed code match up with type annotations. And so what can happen is that a value of unexpected type can show up in typed code all of a sudden and start causing problems. At best, causing a primitive safety check of the underlying language to fail. Perhaps saying like, there's a method on this value that's not defined. And all the developer gets to help them debug in that situation is a simple stack trace from the failure of that safety check. And the academic argument here says that this is unsatisfying, and that really there should be some dynamic checks that are enforcing the meaning of types as the program runs. And while many different ways have been proposed to do that, we can broadly bucket many of them into two major alternative semantics. First of which is the natural semantics, which translates type annotations into higher-order contracts that dynamically ensure that values match up with type annotations wherever the type checker can prove that's going to be the case. And when those contracts do detect a problem, they also provide this specialized debugging information called blame, which identifies one boundary between typed and untyped code in the program as being at fault for the mismatch between this untyped value and these type annotations. The transient semantics, on the other hand, takes a different approach entirely. And it goes and rewrites type annotated code to insert these inline type assertions that check the type of values in typed code as it runs. And transient provides its own flavor of blame. But this one identifies potentially many boundaries in the program as being possibly involved with the fault. Now, of course, these alternative approaches come with performance overheads because they do all this extra checking and they do all this extra error tracking. But maybe it's worthwhile if the extra error information they provides debugging benefits. So now we have the context to state a more refined research question, which we're really interested in here, which is, given the same statics, which semantics for gradual typing provides better error information for systematically locating type interface mistakes? Now, to understand this question and how we investigate it, it's important to understand concretely how the different semantics compare in terms of the debugging information they offer in the face of type interface mistakes. So let's look at a small example that illustrates the differences in an imaginary Python-ish like language. And in this example, we have an untyped library called JSON unpack. We have a type interface for it, which declares that it provides one function of the same name that accepts a JSON object and it returns a list of hash tables. On the client side, we have an untyped main component, which imports this function, calls it, and then passes the result off to a helper function to process the result. And that helper function is itself defined in a separate client module, which is typed. And all it does is takes the data apart, iterating over it using the appropriate list iteration forms and hash table lookup operations. All of this under the assumption that this data has the result, or has the shape described by the type on the interface. Unfortunately, that type is wrong. JSON unpack doesn't actually return a list of hash tables. It actually returns a list of association lists. So now, let's see what happens if we run this program with each of the three semantics, starting with erasure. So in this example, the type annotations here don't help the type checker to identify the problem. So when we run the program with the erasure semantics, the program might crash, at best, perhaps in the body of the helper function, when trying perhaps to use a hash lookup operation on one of these entries, which isn't actually a hash table. And in that case, all that the developer gets is this stack trace, identifying the main and helper components here. Now, under the natural semantics, this exact same program with the exact same type system would have a different result. The type annotations on the type interface would become a contract, ensuring that the result of JSON unpack is actually a list of hash tables when it's called, and that check would fail. And natural would provide its special blame information, which would identify this boundary between the JSON unpack interface and the untyped library itself. Because clearly there's a mismatch between the type on the interface and the actual value returned by the function. Finally, under the transient semantics, this same program with the same type system has yet a third result. Transient goes and rewrites the typed helper function here, and it inserts inline type assertions. One right at the start of the function body, which asserts that data is a list, and then one right at the start of the body of the loop, which asserts that each entry is actually a hash table. And that last assertion fails. And so transient provides its own kind of blame, which in this case identifies a boundary between the main and helper components. So this simple example already makes clear that there are significant differences in the error information that each of these semantics provide in the face of type interface mistakes. And so our research question is, how do they compare if one's trying to locate the mistake in this program? And to understand this question, we really need to do a systematic investigation and comparison of how the different information each of these semantics offers relates to type interface mistakes. And my collaborators' prior work, published at ICFP and Popple before that, lays out a framework for this kind of investigation called the rational programmer. And the ICFP paper in particular describes how the rational programmer framework can be used to create an experimental method to evaluate and compare the value of error information for locating bugs in gradually typed programs. Now that paper focuses on mistakes in code only. And so in this work, we're investigating the flip side of the coin, where the mistakes are in type annotations, hence the part 2 in the title of the talk. But the main point here is this experimental method, which consists of 4 pieces. First, we formulate a hypothesis about how error information systematically relates to the location of bugs. Then, we design automated procedures that reify that hypothesis, putting it into action to try to automatically locate bugs in a program. And with those procedures in hand, we then perform a large-scale experiment, testing how successfully they're able to locate bugs in real programs. And the result of that experiment is data, providing evidence that either supports or refutes the hypothesis. We can use this data as a basis for comparing the different semantics with respect to our original hypothesis. So now in the rest of the talk, I'm going to go through each of these pieces in turn and talk about how they look in this setting where we're investigating type interface mistakes. Starting with the hypothesis. In one sentence, the hypothesis we investigate is that error information can be translated into the location of type interface mistakes by using the type system itself. In other words, we can locate the cause of the problem by adding more type annotations to the program, guided by the error information available to us. So to develop intuition for this hypothesis and why it's reasonable, let's return to the example that we were just looking at, with the natural semantics here, where we had this blame identifying this boundary between the type interface and the untyped library. We got this blame because there's a mismatch between the type in the interface and the actual result of the function of JSON unpack. And the idea here of this hypothesis is that we can use the type system itself to get more information by annotating the untyped part identified in this error message, turning JSON unpack into a typed component. And then we can try to run the program again. And if we do, we'll find that the type checker doesn't allow us to. It raises an error which directly identifies the mismatch between the actual type of JSON unpack and the type on the interface. So that's the idea of the hypothesis concretely. And at least for natural, this example seems to support our hypothesis. Let's see the case with transient. We can apply the same reasoning here, but using transient's blame instead of natural's. And so we start with this blame that transient provided between the helper and main components. And again, we looked at the untyped side here and annotate main, turning it into a typed component. And we try to run the resulting program. And in this case, the new type annotations don't help the type checker to decipher the problem. So we can run it, and we'll get a new error message from transient with new blame, now identifying this boundary that we had before from natural. And so we know if we repeat the logic here, then we'll again get to a type error. And so we can say that for transient, again, this example seems to support our hypothesis. With erasure, unfortunately, we're not so lucky. We do have this stack trace identifying the main and helper components here. Therefore, we can select the untyped component here and equip it with types and try to run the resulting program. Unfortunately, adding these new types doesn't affect how the program runs. That's the whole point of erasure. And so we get the exact same error message. And now, the error message gives us no pointers about how to proceed, according to our hypothesis. And so here we can say that at least for this example for erasure, our hypothesis does not seem to be supported. So now we have a concrete sense of this hypothesis and why it's reasonable. The next step is to reify it in an automated procedure. And what that procedure is going to do is essentially what we just did with the example. It's going to go and run the program to get an error message. It's going to identify the untyped part of that error message and try to add type annotations to that component. Now this third step, it might fail if, for example, there is no untyped component identified by the error message, like we just saw in the example, or some similar situation. And in that case, we say that the procedure overall fails to locate the cause of the problem with this program. Now there's also a small asterisk here, because if you're really thinking hard about this, you might be wondering, hey, how are you going to go and automatically type an arbitrary component? But hold that thought, I'll get to that in a minute. Okay, so in the case that we can type the component, the procedure goes ahead, it type checks the program, and if it type checks, we can go back to step 1 and repeat the process from there. If it doesn't type check, then we got a type error. And in that case, we say that the procedure succeeds because it translated this dynamic error into a static one that should identify the problem. Now, of course, we saw from the example that really we can make versions of this procedure that use each of the different semantics that we're interested in testing, not just the natural semantics, and it just adjusts slightly to use the corresponding error information they provide. So really, we get a family of these similar procedures that essentially do the same thing. Now, one problem here is that natural and transient, they really actually do two things differently than erasure. On the one hand, they do all these extra dynamic checks to ensure that runtime values match up with type annotations. And if those checks detect a problem, they also provide this special blame information on top. And really, these are two differences that we'd like to be able to separate so that we could isolate the effect of having dynamic checks in the language from the effect of having blame on top of them. And to do that, what we can do is just create two more versions of this procedure that use the natural and transient semantics, so they have all the corresponding dynamic checks, but they ignore blame information. And they simply use the more basic stack trace that also comes alongside with these check failures. It's important to note that these stack traces are going to be different from the ones that you'll get with erasure, because they'll come from failures of checks that erasure doesn't have. Okay, now finally, as a small piece of terminology, we call each of these versions of the procedure modes, and the relative success and failure of these modes in the face of real programs with bugs will give us a quantitative understanding of the comparative value of the information that each mode is using to try to locate bugs, at least with respect to our hypothesis. Okay, so now that we have these procedures, we're ready to design an experiment to test them out on real programs. And of course, the challenge here is to obtain suitable programs with type interface mistakes for this experiment. And for that, we start with the GTP benchmark suite, originally used by Ben Greenman and collaborators to evaluate the performance of gradual typing in typed racket. And this suite has a couple of features that make it a particularly good starting point for this experiment. First, it's a diverse corpus of programs written by various authors, originally for various practical purposes and in various different styles and so on. And secondly, it has this property where every program in the suite has interchangeable typed and untyped versions of every component in the program, such that you can select either the typed or the untyped version of each component to get a concrete configuration of the program to run. And this actually has the important effect of allowing us to trivially automate that step of our procedure where you have to type an arbitrary component that might get blamed. Finally, the suite's also written in typed racket, which, thanks again to Ben Greenman, is the only platform that has implementations of all three semantics under the same language, the exact same type system. Okay, so from this starting point, we then use mutation to inject synthetic faults into the programs, transforming the suite into a large corpus of possibly buggy versions called mutants, each with a single known potential bug. Now, of course, in this setting, we're interested in bugs in type interfaces, and traditional mutation expressly targets code and tries very hard to avoid introducing type-level mistakes. So for this, we need to design and evaluate a new set of mutation operators that target the language of types. There's actually a lot to be said about how we designed and evaluated those mutators and how we go from these mutants then to concrete scenarios that are suitable to test in the experiment. But for the sake of time, I have to skip over those details. Please go to the paper if you're interested or talk to me afterwards. And I have to skip ahead now to the results of running the experiment. And the main kind of data that we get out of an experiment like this can be visualized in this way. This plot is a summary of the comparative success of each mode against all of the other modes we tested. There's actually quite a lot packed in here, so I'm going to just spend a few seconds talking about how to read it. So at the top, there's the name of a mode we tested. And this mode's being compared against all of the other modes along the x-axis. And for each such comparison, there's 2 bars. So if we zoom in on one of them, for example, here's how you read it. The green bar above the 0 line is the percentage of scenarios where the mode at the top succeeds, but the mode at the bottom fails. We can interpret this as the percentage of scenarios where the information that the mode at the top uses was more useful for our procedure than the information that the bottom mode uses. Now the red bar below depicts the inverse percentage. And so you have these kinds of comparisons for all of the modes we tested. And you can create this kind of plot for all of our modes, and the full data is in the paper. But here I just want to highlight a few key observations, starting with how blame stacks up in this world of type interface mistakes. Here's the data for natural with blame. A quick glance is enough to see that natural's blame has significant debugging benefits in this space. It's able to be translated by our procedure into the location of the bug in 20 to 40% more of the scenarios than all of the other modes that we tested. Transient's blame, on the other hand, has more mixed success. And in particular, it only improves a bit over transient without blame, or even erasure. And in stark contrast, natural and transient semantics that do dynamic checks but don't provide blame fare miserably. And in particular, I want to highlight that they provide either significantly worse information than erasure for our procedure, or information that's on par with erasure. So all these results together, they suggest a few takeaways, or really questions that bear further investigation. First of all, considering the overwhelmingly poor value of the error information provided by the natural and transient semantics that do dynamic checks but don't provide blame, the question arises of whether these kinds of semantics make sense, practically speaking. Second, natural's strong success demonstrates a very concrete connection between the blame information it provides and locating type interface bugs. But it's also well known that natural has often prohibitive performance overheads. So this trade-off between the debugging information that one gets and the performance overheads is unclear. But it's worth noting that this coincides with the results of our previous investigation, which found the same thing for code mistakes. So still the question seems unclear. And to that point, I want to share one last insight, which is that we asked one more question of our data, which is what if we separate debugging from bug detection? In other words, how often does each semantics raise an error, any kind of error, to indicate that there's a problem with the program, as separately considered from whether you can use that information to locate the bug? And what we found is that for the bugs and scenarios we tested, erasure is able to detect the vast majority of the bugs. It's pretty much on par with the other semantics, about 5% lower. Now that suggests one last takeaway, which is that perhaps erasure suffices for production use. If there does end up being a type-related problem, it seems likely that erasure can detect it and raise an error. And then perhaps natural with blame has a role to play as an offline debugging mode, where developers can try to reproduce the problem and debug using the extra information natural offers without necessarily having to worry about the performance overheads as much. So I'll leave it at that. Thank you for your attention. I'm happy now to take questions.
Questions, please come up to the mic.
May I ask a question? Hello? Hi, Will Creighton from Brown. So I'm a big fan of lightweight usability methodologies that don't rely on humans, but I also think that it's really important that we have, like in psychology, they call it validation on an instrument like that, where you have evidence that these non-human methods correlate with some kind of psychometrics that we care about. And so I'm curious, what would be your argument as to why this is a valid proxy for real human debugging behavior, as opposed to, alternative ways that people might interpret the information given to them by the CLI that wouldn't correspond to the process prescribed by your rational programmer?
Absolutely. Yeah, so it's a great question. And I think at one level, my answer is a bit of a cop-out, because it's that I wouldn't claim that this corresponds in any way to what real developers do in the face of error messages, and whether this information is helpful for real developers to look at it and think about what to do and then eventually find the bug. Rather, I would say that this investigation is about, are there systematic relationships between the information in the error message and the location of bugs? And this is kind of being separated in this experiment from the also extremely important question of, is that connection useful, right? Like, if you show a programmer this error message and this connection holds, is it a useful combination for them to find the bug? And I think that demands separate study. So I would say very important. It needs to be done.
Okay, thanks.
Max New, University of Michigan. I have a question about generalizability of this to different kinds of languages. So specifically thinking about erasure semantics, Racket is a great language in that if you use most of the built-in libraries and you have a type error, it will actually result in a runtime error, right?
Yeah.
Whereas in a language like JavaScript, it's very likely that there's a logical type error, but it will go on for considerably longer. There may not be any runtime error at all, right?
Yeah.
So I wonder if you had any thoughts about evaluating this for JavaScript, and if you think this specifically, that the erasure is catching most of the bugs, would generalize to these other semantics.
Yeah. So it's a great question, and absolutely, I think that's an important thing to point out, that typed racket and racket underlying, right, has all of these safety checks everywhere. That in JavaScript, it's more of the attitude is like, well, that went wrong, let me just put undefined or something like that, right? And then it can kind of propagate. Yeah. So I think really that demands a study with JavaScript, I think. And so the question of whether this natural debugging mode makes sense in the context of JavaScript demands another study, I think. The interesting thing about TypeScript, typed racket is that their type systems are pretty similar. They have interesting advanced features that they share. So in that respect, that's good for generalizability, but I do think a separate study is needed.
We're running short of time, so maybe we can have one more question while the next speaker is setting up.
Sure.
The next speaker
I'll give it to Sam.
is remote. Thank you. And are we set to go with the next speaker?
More or less.
Okay, so quick question.
Sam Silverhawks at Indiana University. So thanks for a great talk. I think one thing I just wanted to comment is, it seems like your results give us some insight into why natural is expensive, and in particular, the results of the natural exceptions being useless tells us that what natural is doing is it's connecting information across a long distance, because otherwise the blame and the stack trace would have closer connection, and it is
Right.
So this nicely demonstrates that there's something fundamental about that distance in what blame is doing in a natural system, which is why there's sort of an ineradicable form of performance overhead. So I really appreciate that for clarifying that aspect of the landscape.
Great. Yeah, I agree. So I think that's a good insight. Thank you.